everybody. So we're continuing with area moments of inertia, this time using the parallel axis theorem to solve problems where you have a shape that's a composite of other shapes. So for this example here, I have what looks like a triangle stuck to a square. So I got the entries for a triangle and a rectangle out of the appendix. And let's give it a try. Let's say we want to solve for the moment of inertia about the x-axis. So that means rotate this composite shape about this x-axis. So if you rotate the triangle about the x-axis, that is, for the triangle, here. And if you look in the appendix, that's like rotating the triangle about this axis here, which happens to be given. Okay, so for the triangle, so about the x-axis for the triangle, we know it, 1/12 base height cubed for the triangle. So 4 times 3 cubed. Okay, now for the square, that would be rotating about this x-axis. If we look in the appendix, that's just like rotating about this x-axis, which is here. So we know it. For the x-axis, for the square, 1/3 base height cubed. So 1/3, 3 times 3 cubed. Okay, so that maybe wasn't so bad. Now let's try about the y-axis. So that's like rotating it about here. So for the triangle, rotating about the y-axis is just like how it looks in the appendix. So about y, for the triangle, we know it, it's right here, 1/4 hb cubed. Okay, now for the square. So the square is here, and we want to rotate about the y-axis here. That is not how it looks in the appendix. Right, we have a rectangle here, and we want to rotate about an axis here, which is 4 feet away from the edge. I'll call this maybe capital Y. Okay, so in the appendix, we know the answer here. So we can move to here, but here is where I have to point out, you have to be careful. The parallel axis theorem is with respect to an axis through the centroid. So in the y direction, we don't want to go from here to here. It has to be through the centroid, this one. So let me label these. How about I call this, so this is y prime through the centroid. I'll call this y1, and I'll call this y2. Okay, so it is correct to do something like this. Plus extra, right? So for this axis, with respect to this axis, it would be 1/12 hb cubed plus extra. How much extra? Here to here squared times the area. Or you can go like this. If you want the moment of inertia about y1, then it's 1/12 hb cubed plus this distance squared times the area. That's okay. What is not okay is going from y1 to y2. This is not okay. We can't go from here to here. Neither of those is going through the centroid. So that's not okay. So I'll make a big deal of that. Be careful to not do that. Okay, so back to this particular example. We want the square, the centroid is here. Right, so it's not okay to do parallel axis theorem from here to here. It has to be from the centroid to here. So that's 5.5 feet. So then for the y-axis for the square, this is 1/12 hb cubed from the appendix plus extra. How much extra? 5.5 feet squared times the area of the square. This. Okay. Now let's try the product of inertia. So the product of inertia, let me make some space. Okay, so for the product of inertia, for the triangle, that is about this xy axis, which if you look in the appendix is just like here. So it's okay if we use this entry for the triangle. Okay, but then for the square, if we look at the appendix, we can't just use this entry here because that is about this axis, which is like here. So we can't just go from here to here because that's not the centroid. We have to go from here, the centroid, to here. Okay, so for the rectangle, it's about the centroid, which is this entry, happens to be 0, plus extra. How much extra? Here to here, 5.5 feet, times here to here, 1.5 feet, times the area of the square, 9. This happens to be 0. Okay, so this is the product of inertia for the composite. Okay, one more application. Let's say you want the centroid of this composite, and then the moment of inertia about the centroid. So let's say the centroid is somewhere. Well, let's figure out where the centroid is first. Okay, so it's like here, here. So for the x component, where is this? That's 2/3 of the way over, right? 2/3 of 4 feet times the area of the triangle. So 1/2 base times height. So that's 6. Plus, where's this for the square? The centroid of the square. That's 5.5 feet. Right here to here. Times the area of the square, 9. Divided by the total area. Okay, so we got the x component of the centroid. For the y component, here to here, so that's 1/3 of the way up, times the area of the triangle, plus here to here, the centroid for the square, 1.5, times the area of the square, divided by the total area. Okay, so we got the coordinates of the centroid for this composite object. Let's say it's somewhere over here. What's the moment of inertia? Let's say about x prime, y prime. How do you do that? We already solved for ix and iy and ixy. So how about here and here? ix prime. Which of these is more? We solved this one earlier. We're looking for this. So let me switch it around the other way. this is less, this is more, right? Because about the centroid is a minimum. So that means minus some extra. How much is that? The distance between these two axes, between x and x prime, right? Which is this answer we just got right here, times the area of the composite. Okay, how about y prime, about this axis? We already solved it for this one, and we know that this is a minimum, this is more, so it's minus some extra amount. How much is that? The distance between here and here, which is this, the x component of the centroid. That squared times the area. Okay, and then how about the product of inertia? Again, that's a minimum. This one is more, we just solved for that earlier. So it's minus some extra amount. How much is that? This distance times this distance times the area. So there, that's how you would get moments of inertia for the composite about axes through the centroid. Okay, so that was a lot of information. Just practice. And then I have to point out one last thing. What if there's a cutout? Like say I cut a hole over here. A cutout. So you just treat a cutout as a negative moment of inertia. Right? So whatever, like this is a triangle, a square, and then another small rectangular cutout, we just treat this moment of inertia as being negative. Okay, so I hope that's helpful. Let me know if you have questions, and I'll see you on the next video.